Spatial resolution. Spatial resolution describes the size of individual measurements taken by the remote sensor system. This concept is closely related to scale. With an analog sensor such as film, the spatial resolution is commonly expressed in the same terms as the scale. Since digital sensor records information in raster format, the spatial resolution is the cell size and ground units. See spectral resolution. Spectral resolution describes the sensor system's ability to distinguish different versions of the EMR spectrum. Some sensors are sensitive to visibly light only. A panchromatic band is a wide band that encompasses a large spectral length range, often the entire visible spectrum. When a sensor records only a few portions of the spectrum, EI contains only a few relatively wide bands. It is said to be a multispectral system. A multispectral sensor might have two or three bands in the visible range, red, green, and blue, and it might also have a few near-infrared or middle infrared bands. Typical multispectral systems have between 4 and 10 bands. Each band, a digital dataset, can be thought of as individual raster layer visualized and image the three dimensions, with rows, columns, and bands filling the x, y, and z coordinates of a curve. Radiometric resolution. Radiometric resolution describes the number of unique values that can be recorded by a sensor system when measuring reflected or emitted EMR in a digital system is usually quantified as a number. Converting remote sensing data into geospatial data. Remote sensing applications are rarely successful without at least some direct measurement ground. However, that is really a misnomer since there are always at least some error in measurement. Even if they are taken directly, ground reference could be a better descriptor. A correct term for measurement taken directly as opposite to remote measurements is in situ data collection. Several types in situ measurement may be necessary for a given project or application. Almost all remote sensing projects require some amount of in situ data collection in order to perform geometric and radiometric calibration. Geometric correction. When remote sensor data is initially collected is not geospatial data, in order to make the transition to geospatial data, geometric correction must be applied to make the data into a real-world coordinate system. Beyond having no real-world coordinates as finds, the raw data also contains geometric distortion. This means that all of the objects or phenomena that can be seen in the data are not equally outplaced relative to a desired coordinate system. Distortion is therefore different depending on the sensor configuration. Example: scanning mirror sensor versus area array digital cameras. A basic method for geometric correction involves the use of a GPS receiver. In the file, GPS measurements are taken at locations that are also easily identifiable in the imagery. Once analog control points have been collected, they can be used to adjust the data's approximate spatial position within a coordinate system. Most geospatial software packages provide an interface for doing this. As part of the process, the software packaging will typically report a number indicating radiometric correction. In addition to geometric distortion, EMR that is received by the sensor contains radiometric distortion. The source of the distortion is primarily the atmosphere and dynamic constituents. There are various ways to minimize this distortion between data. Radiometric difference can be minimized if the datasets are collected at similar times so that in addition to geometric Even after taking these measures, many applications require additional radiometric correction to account for difference and distortion. One simple radiometric correction technique is to rescale all of the pixel brightness values in image by identifying one of the darkest pixels. This method is more complex than either of the previous two. It relies on collecting explicit information of the environmental condition at the time of the remote sensor data acquisition. Process the remote sensor data along with the ancillary data to produce a radiometrically corrected image. Visual image interpretation with the power of the human visual system, much information of in remote sensor data can be acquired simply by visual inspection. In this case, a trained image analysis uses a combination of real-world experience and heuristic rules of thumb to interpret what is seen in the image and determine its significance. The process of image interpretation can be broken down into its fundamental elements including point 1 absolute location or coordinates, point 2 relative location, point 3 size, point 4 shape, point 5 shadow, point 6 tone or color, point 7 texture, point 8 pattern, point 9 three-dimensional characteristic, and point 10 color composite. Automated classification. Although manual image interpretation is valuable and often provides highly detailed and accurate information, many applications require the objects on the ground be classified faster and more cost-effectively. There are primarily two different ways to approach this goal, but they based on the simple concept that similar objects or phenomena have similar spectral reflectance properties. The first method is referred to as unsupervised classification. Mapping spatial variables. There are certain aspects of phenomena that must be sensed while direct contact with an object. For example, it is impossible to directly measure the live biomass, the amount of living matter present in a stand of vegetation without harvesting in the vegetation. Mapping biomass requires taking some in situ measurement of the vegetation of interest. These measurements are used to build a mathematical model relating to the quantity of biomass to the spectral reflectance. Creating elevation data from remote sensing data. A second related method is radar interferometry. Difference in radar signal acquired over the same area from different positions can be used to create an elevation surface. A third method of deriving elevation data is to use LiDAR data. Most of the time, the collection of LiDAR data results in a series of XYZ points. All data from remote sensing is often valuable because it may provide only long-term data for a large extent of geography. Remote sensing software. The most used software in remote sensing are ESRE, Environmental System Research Institute, ERDAS, RSI, ANVI, MapInfo, Mapper, Autodesk, etc. The most free remote sensing software seem to be chips. Application of remote sensing and GIS. Remote sensing is an important tool to provide important information on soils, land evaluation, land degradation, crop distribution, crop growth, availability of water resource, etc. The information of remote sensing can be improved into efficiency by combining with conventional technologies. Thank you.